Ah, hello. I'm Rami. I'm a senior engineer at Qualcomm, and with me is Devin. Devin, would you like to introduce yourself?
Hi, I'm a U student at UC San Diego, and I worked on this project with Rami.
Cool. So with Qualcomm chipsets, a lot of times it's pretty difficult to get things up and running, especially to run on the NPU, and things get a little bit complicated. But we kind of created a way or found a way to make things a little bit easier to get people started. And Devin got to write most of this code, and he's just going to walk us through how to use TensorFlow. But before that, Devin, how did we get introduced?
Yeah, so Rami was a mentor for our first robotics team at my school, which I was a part of. And so I was on the sort of programming part of that team, and Rami helped out a lot with that. And so that's sort of how we got introduced.
Cool. What are you studying at UCSD?
Computer science.
Nice. And then any fun projects you're working on or
Well, yeah. So in my spare time, I've been doing some stuff like re-implementing the internet protocol with Rust. Um, uh,
nice. Super complicated. Hopefully nothing this complicated here. But yeah, why don't you take us along and show us what you've done?
yeah. So I can go through the code first, or I can go through the sort of build and setup process first.
Just go through the code first, I think.
All right. So first, there's the model input and output. So of course, this would be programmatically acquired, but here it's through the command line. And so the first thing is setting up the TF-Lite interpreter. And this is what's actually doing all the work. This is the important changed part here. So the delegate options that you're passing, the backend type has to be HTTP, and then you load the QNN SO delegate file. And so this comes pre-installed on those NPU devices. And so this should just work. And then once you instantiate the interpreter with that parameter, you can then allocate the tensors, and then you can start setting up the model. And so you need to get the sort of input and output tensor information. And then this is all just debug info. So you'll see how that works in a second. And then there's also the extracting the dimensions of the tensor. And so that's just this function here. It checks all the different possible combination of shapes. This would probably be hard-coded in if you're using some sort of hard-coded model. And then once you do that, you have to load the input data for the tensors. And so we're just using the Python image library here to load a file, and then confirming that the shape of the image matches and converting the color space if it doesn't. And so this, again, is something that you'd have to hard code depending on what your model is specifically. And then converting the data types. And once you do that, you can just take the data and you want to get it as a flat byte array. And once you have that, you can just set the data into the input tensor like this. And so this is kind of the input step of the entire processing loop. You're going to fill the input tensor with byte data. And then this is what actually does all the work. Invokes the interpreter running the model. And after that, all the output data will be in the output tensor. And so this returns that data as a NumPy array, which you can then construct an image from as output. If it wasn't image data, then of course you could load it as text bytes or tokens or audio data or whatever that would be. But in this case, we'll load it as an image, save it to a file, and that's actually it. And there's actually a C version of this. It follows a very similar flow. You load the interpreter, you add your HTTP delegate options, you invoke the interpreter after filling it with data, and then you have your output data.
So something to kind of point out, what kind of model are you writing this for?
Yeah, so this is like an image transformer model in this case. And so that's why we're loading the input image. It's the ESR-GAN model. And so you can see the full name right here. All these models should be on the Qualcomm AI Hub. And for this specific, the Rubik Pi NPU, the 8-bit quantized version performs best on the accelerator chip.
Nice.
So I can go through running that now. So first, you're going to set up a virtual environment. And so you set that up like that. And then activate the virtual environment. All right. And then now the dependencies, it's actually pretty light. So you only need TensorFlow and NumPy. And then Pillow is just what we're using to load the input image. But if you're doing this sort of frame by frame real time, you probably want to use some library for loading data from a camera or webcam or something like that, maybe even a network stream. But then to install that, you can do, I actually don't remember how to exit this. And then on the C side of things, it's very similar. It just uses CMake, and so you just need to install those dependencies by yourself, install the package config files, and then CMake should pick those up. Now the Python mode is done. And so we can take the demo file and then just call it on input. So I took this 128 by 128 image of a cat here. And then we're going to try and upscale it using the ESR-GAN model. So I believe the order is that. Might be backwards.
I think it is.
It's backwards. Okay. Oh.
I think you need an output name.
Oh, yeah, right. Okay, so I'll just create an output PNG. All right, and then it's running. So the model setup is what takes the most time, but we'll see some timing values once we actually run it and once it's loaded onto the device. All right, so as you can see, the actual execution time of the model is 120 milliseconds, and that scaled it up from a 128 by 128 image to a 512 by 512 image. And if we look at the output PNG, you can see that it's bigger and, well, higher resolution. And yeah.
Why don't we, sorry, I'm going to put you on the spot, Devin. Can we try removing the HTTP backend and then running it and see the
sure, yeah.
time?
And so that will, I mean, we can make it explicit and set this to the CPU backend.
Yeah.
And so that will just run it on the CPU instead of the NPU. And we should see loaded a lot faster, as you can see. But once you invoke the interpreter, it takes forever. And so, you know, in total, it's faster for a single execution. But as you execute it more and more, it's going to get faster and faster with the NPU version.
So I think we also kind of forgot to point this out. So this is all running on the Rubik Pi. So the Rubik Pi is the 6490. I should probably unblur. The 6490 chipset. So this is one of the Qualcomm IoT products. This board is made by Thundercom. It's a very nice single board computer that is pretty cheap and available on the Thundercom website and makes things super easy for development. Yep. Any questions? If nobody has any questions, we're just happy to demo this. Thanks, Deven.
All right. Thank you.
Have a good day, everybody. Oh, so we got last minute questions.
Oh, yeah. All
Is
right.
it possible to see some details on some NPU memory utilizations, which I think get printed out, right, Deven?
Yeah, let's see. Well, let's just go through the logging here. So bandwidth summary, and doesn't look like it showed anything during execution, but it might have here. I can try and get some verbose logging up. I actually don't know how to do that, not in the C version. Let's see. Do you know what the fastest way to get the...
I was actually going to showcase the AI Hub here. So if you go to AI Hub,
that should have those details.
It'll have every single detail. So let me see if I can share my screen as well.
I can also pull that up.
Yeah, please.
I may have to change the share. All right. Okay, so if you, I'm not sure why the screen sharing isn't showing up right now. All right, and so you can see on the Qualcomm AI Hub, this is the specific model that we're using here. And so you can see all the statistics. And so this is pretty easy because you don't have to actually benchmark it. They've already benchmarked it for you. So this is the specific chipset of that board. And you can see that inference time, this is actually not correct. But the memory usage, actually, do you know if this is a different model? Not quite sure.
4x.
Oh, yeah. It's the X4 Plus. So this is actually a different model. Okay, so you can just search the models here. There's a bunch of options. There's okay.
There you go.
Yes, this is the one. This looks more correct. So you can see the W8, that's the specific quantized model that we want. And that looks correct. And so you can actually see the throughput. So you can do this, at 9, 10 FPS. And it uses about 250 megabytes when it's loaded into the model, I assume. Do you know if that's correct? Is that during inference, or is that just when it's loaded?
That is once it's loaded.
Okay. Yeah. And then the TF-Lite is the one you want.
Yeah. If you click the see more metrics, you can see a lot more details about this. And then you can actually, let's see if I remember how to do this. Yeah, I mean, there's every single memory aspect at every single one, and you could do an even deep dive into the actual model layer by layer.
Yeah.
But if you scroll up, Deven, there you could see like the detailed metrics, first upload, subsequent upload, and the inference time in both time and memory for each one.
Yeah, so that looks about right. It takes a while to load, but then the inference is really fast. And then, yeah, the spec of the board is this QCS 6490. That's the chipset for the NPU.
Llama is, so large language models are currently not supported on the 6490. So the question was, what exactly do we put in the target platform? So for the target platform, you can usually put either 6490 or the RB3 Gen 2. It's actually the same exact chipset. But the large language models are not from AI Hub are not actually supported on the 6490 chipset yet. Be on the lookout. There's going to be another build along where we're going to do LLMs on this IoT device, but that's targeted for another session. Any other questions? All right, if there's no other questions, I think we're happy to end early. Thanks everyone for giving us a little bit of time this morning. Thanks, Deven, for showcasing this. Good luck at UCSD. And you please keep asking questions on the Discord. I'm available. You can find me at Rami_Qualcomm. There's a lot of other experts that can answer some of those questions. Thanks, everyone. Good day.
Thank you.
Bye.